So our next topic is maintaining design integrity from procurement through installation. So as design engineers, basically we're designing in a perfect world. All the material is exactly what it's supposed to be. All the tolerances are perfect. The welds are always perfect. There are no flaws. So, but there's a reality there, and so if our design engineers do their job, then there's a lot of other steps that we have to basically maintain to make sure we meet our expectations. It's not just the engineering and then you kind of hand it off and it's all good. So I thought this would be a kind of a good exercise to kind of go through some of that process and some of the realities of what we see, what's the impacts of that, and kind of some of the sort of steps to take to try to get what you expect. So here's general outlines to kind of give you a quick overview of some of the materials. We're going to talk about project planning, goals and expectations, issues that compromise design, as well as we'll go through the design fundamentals, and that's probably the biggest part of this, and then kind of steps to maintain the design integrity of your equipment. So here's some of the equipment that we're talking about. So a lot of large diameter tanks. You got horizontal process vessels, piping. Some of that's fiberglass, some of it's plastic, and PVC probably there. Stacks, for example. So a lot of different things, different design processes to think about. So from a project planning standpoint, this is kind of the steps that we feel like are important. I kind of pointed to this a little bit earlier, is that when we have specifications, we want to have current specs. We want to have, for example, like for FRP piping, we have NN2 came out from ASME in really 2019. Still not updated into a lot of specifications yet. So if you get something before that, really you're sort of in kind of a no man's land of trying to squeeze FRP through B31 or 3 or something like that, and it can be a real challenge. So updated specs, I'm kind of wanting to qualify in vendors. Some vendors are good at piping, others are good at tanks. There's a few that are good at both. But you want to know who's who. Everybody will say, yeah, we do that too. Usually when you hear that, that's usually not a good thing, because it takes a whole different set of tools to make pipe versus tanks. And then obviously, we want to have good design and engineering in everything we do. We want to have QC checks. That's QC checks in engineering as well as all the way through the manufacturing process. Particularly piping, when it comes to site, we want to have QC during installation as well, and obviously testing and startup. So expectations. So obviously, we always expect high quality. We want to maximize performance. We want to have a reliable system. We have, it's an important process that our equipment's going in, so we want to make sure that it operates like it's expected, it's consistent, there are no issues. We want long run time, just like I talked about before. And generally, whether or not we're designing piping or vessels, ideally we want to be designing for a 20+ life expectancy. There are a few services which that's kind of challenged, like chlorine is one where it's very aggressive to FRP and non-metallics. So generally, depending on the service, and what materials you choose, who does it, we see anything from 12 to 20 years is probably on the outside. We see a lot of 15 to 17 if it's done well. But generally, as far as an approach, we're trying to take steps to get that 20. So obviously, expectations, it's brand new when we get it, so we're expecting it's all going to be good for a very long time. So, one thing I want to point to is, beware of low price. It's a very common discussion that I hear that, I went out to 4 bidders and this one really looks really good. We think we're going to go with them. They're 30% cheaper than everybody else. And they're you know, maybe they're even a certified shop, but I mean, the reality is, and this is probably one of those, like, we'll build to RTP1, but we're not gonna stamp. If somebody is that much cheaper than everybody else, you know, it's like, what are they leaving out? Because it ain't gonna be the same. You know, either the materials are gonna be different, they're gonna cut corners, they're moving faster, so maybe they're not grinding as much. Who knows? But I can guarantee it will not be the same. It just, you know, in just about anything you do, you're not going to see that big of a difference. So if that's okay, if you don't have a critical service and you're not worried about spilling a little water on the ground or whatever it might be, then maybe that's not a big deal, and maybe it is a good deal for you. But if it's critical service, you have to worry about safety and performance, then, you know, just be aware that, you know, all things may not be as equal as they appear. So some issues that compromise design. So some of the biggest things we see is understated design conditions. We might see a operating pressure specified instead of a max design pressure specified, which operating is what it normally operates at and what we expect it every day to be, but the max might be, you know, a pump shut-off or something like that, where a pump runs up before it trips. You know, what can that pump possibly produce? That's generally where the design pressure is a lot of times, and you know, other things might be max temperature. You know, the same kind of thing is we specify this, but we find out that, well, when it's being operated, that's not optimal, so they kind of dial up, they'll touch up the temperature to try to maybe get a little bit more product out, maybe make it more pure, something else, and so that kind of thing happens. Also, installation temperatures. You know, as engineers, if we're not told anything different, we take installation temperature generally here in the U.S. to 70 degrees Fahrenheit, ambient temperature. But a lot of stuff gets installed in Iowa in the winter time, and the reality is it's 35 or 40 degrees at best. So if we know that there's going to be a bigger swing than that during installation, that needs to be a part of the equation, especially, for example, if you're doing a pipe stress analysis, because the temperature difference between, say, 35 and 150 is a lot different than 70 and 150. And if you didn't pick up on it, with steel, when we do pipe stress, we're designing from the lowest to the highest temperature, and with FRP, we're designing from ambient to the highest and ambient to the lowest. So that's kind of the key difference there as well. So it does make a difference. And then, you know, beyond that, the next thing is, you know, understated loads. You know, when that gets into external loads, upset conditions, you know, temperature spikes, water hammers, things like that. External loads for vessels might be piping nozzle loads. So you have maybe more predicted thermal expansion from a piping system that's putting stress on a tank nozzle. Maybe it's a valve hanging off the tank nozzle that's not supported, something like that. And then, you know, missing information, things like settlement, cyclic operation, trace elements in the stream, things like that. So other issues that compromise design. And when I say that, it's where you get, they basically say a shorter service life than expected. Is marginal materials. So this would get into, we see it fairly regularly in dual laminates, where a dual laminate lining will be specified. And I mean, you have the whole spectrum of lining materials, and you know, we've talked about thermoplastics. So you more or less you're going from like polypro and PVC to like ECTFE in the middle and PFA on the top end. And you know, this is $1, this is 10, and this is 50. So you know, if you have a choice and 3 people come to you with these materials and they say, well, polypro works for this just as good as PFA. So, well, if I'm the procurement guy, polypro sounds pretty good. But they don't tell you that this one is good for 7 years, this one's good for 10, and this one's good for 20. So that's the kind of thing, that's the reality of what happens a lot of times. Tall tanks have kind of different load sequence. You can imagine taller shells, so you have all this vertical weight coming down. If you got a 20-foot tank, well, that's kind of normal, and that's basically what the design standards are designed around. But if you got a 40-foot tank that's 10-foot diameter, now you get twice the weight sitting on that bottom knuckle. So generally we do FEA on that bottom knuckle to make sure that that bottom knuckle is going to be appropriate. Usually, a lot of times we'll find that we need to add additional reinforcements on that to make sure that it's going to basically sustain for the life and basically be within design expectations as well. Large diameter tanks, as things get bigger, all those rules of things being square and plane and things don't really work out well. So we tend to have to do additional analysis, FEA at times, for large diameter tanks as well. Most of the standards that we have for tanks in general are for basically vertical storage tanks. So you make a horizontal tank, there's not a standard for that. Probably more likely you're going to go to like a pressure vessel textbook and look for guidelines for equations to design horizontal tanks. The same thing if you have internals. If you have a scrubber and you've got packing levels in there with 8 foot of packing and a scrubber, well, that's not something the standards cover either. So now you've got to break down and get into your mechanical engineering practices and break down the problem in simple parts that you can basically do calculations for. So these are things that sometimes get overlooked. Maybe they don't get enough attention. So in piping, poor pipe supports, very common thing. And I'll be talking some more about that tomorrow. Deficiencies in fabrication. So tank shell misalignment. What you see right here, 20-foot diameter tank, and you can see all the boards and the strapping trying to pull it all together. There's about a 3-inch gap there. They didn't get it quite as good as to meet the standard tolerances, so it was a bit challenging. Now you got to talk about NCRs, overcorrected measures, and things like that. Tanks are designed to basically be vertically loaded and things in plane. So as soon as you have that offset, now basically you're introducing a bending moment into that joint, and you're saying, okay, well let's put another 1/2 inch on there, and that'll make it strong enough. Well, it's rare that you're going to do an FEA or something like that and say that's okay. You're going to kind of say, all right, we'll buy that. So that's one of the compromises that can happen. Nozzle repads being too small, the wrong resin. A lot of times we find that spec says it's supposed to be one resin throughout. We see the corrosion barrier as one, and then we've done testing and find the structure is something totally different. But that structural resin's not got the same properties as the other resin. Installation, tank foundations not being too flat. That's another big issue. I mentioned joint alignment with piping as well as are common issues. Fluctuations in operations. We do quite a bit of failure investigations and material testing. We have a lab in our office, and unfortunately I don't think we could fit all y'all in there unless we were just like this probably, and that was about it. Things like cycling. Cycling is bad for almost all piping particularly, and even vessels, large process swings. Like I said, most things are designed to run steady and flat out, and swinging up and down, that tends to fatigue that equipment. The process equipment, I mentioned water hammers, temperature spikes, those kind of things. Changes in the chemistry we see, kind of like what they were talking about before with sulfuric acid. At 93 it works great. Well, but we're pushing the envelope a little bit more, so we changed the chemistry, and now we're running a little bit higher. Well, this material is good for this process up to this concentration, but maybe it's good for 32%, but not 37%, something like that. That kind of thing happens. These are the things that it happens during operation, but it does challenge the material. All right, so we're going to get into kind of some of the fundamentals in designs, and this is basically your typical bell curve. Applies to all materials, all equipment, kind of general design approach. So So basically, so here's your strength curve. Like I said, this is very, very typical here. You got basically, 70% of the load is here, and then you're kind of getting off here. But so here's your strength basically. Here's your load curve over here. You notice that they don't touch here. This is your design factor. So what we're talking about here is, so all these little things that I brought up, these introduce uncertainty every time that we change the material, or we have an error somewhere, or an oversight, or a change in operation, or a blip in the process. These curves will move. This is kind of what I want to kind of talk about. So with respect to FRP tanks, generally we're designing, if you follow the standards, most things apply a design factor of 10. For piping, for combined loading, it turns out to be a 6 generally, or something close to that, depending on, there's different design approaches now in the new standard and N and 2. I will note for vacuum, this number is generally more like 5. And that's like, for example, on full vacuum, so you're really not going to get close to that. But just to kind of give you a kind of a benchmark of what we're doing. So here, so say, so here's some, where does the uncertainty come from? So we talked about certified vendors doing material testing to qualify their material properties. So have the material properties been confirmed? If not, okay, well, so that kind of introduces a little bit. So most of your manufacturers have one design engineer on staff that is doing the calculations. So likely he's checking his own calc. Generally in an engineering company, we would not do that. You always would have 2 sets of eyes on it, somebody else checking it, because everybody would make an error. So if they've got one main design engineer, who's checking his calcs? Most owners, I'll say, and then even some engineering companies are challenged to check non-metallic calculations, because the methodologies can vary a lot. So you need to make sure you have somebody who has experience doing it, understand the standards intimately, or else you're just, at best hoping that that guy didn't make a mistake. And then has the full weight, occasional loads been considered? All those things. So if we didn't confirm material properties, so maybe we're not getting the strengths here. So what that does is basically that slides this curve a little bit closer to the loads. So in this case, okay, maybe we're overlapping 5%, maybe not a big deal. So that 10 goes down to maybe it's a 9.5 or something like that. Not a big deal, but that's what happens. But generally, when we see failures, the reality is it's not one thing that happened that causes the failure. It's usually 2 or more than likely 3 things where you have deficiencies, or you have maybe 2 deficiencies lined up with some kind of operational spike that happens or something like that. So let's introduce a little bit more. So you have reduced components have lower actual strength, maybe due to poor fabrication. So that might be maybe you have a nozzle penetration and the nozzle's placed in there, and instead of having the 1/8 inch gap around the nozzle, maybe it's tight on one side and there's a 1/2 inch gap on the other. So now you're putting the same weld across this 1/2 inch gap, so basically you've introduced the weak point into that nozzle. So if you have nozzle loading, it's probably going to give way earlier than if it would have been made to standard. Deficient design, those sort of things that I just mentioned earlier. Low material properties. So again, so we're reducing the strength here. So we're bringing this curve closer. So now we're going from a 5% chance of failure to maybe it's up to 15 or 20%. So this is when we get NCRs and you say, okay, accept as is. This is the reality of what's happening here. And sometimes there's not a good solution. It's not like we can just replace it and start over from scratch. Sometimes you have to accept that. but you need to understand what the realities are, you know, of these choices. And as owners, a lot of times you're asked to accept a lot of things. So here we're going to look at it a little bit differently. So when the structure has more load, so we talked about like thermal expansion and nozzle loads and things like that earlier. So you introduce that on top of the fabrication flaws. The misalignments that I showed you, again, that's introducing bending moments in there. Workmanship issues, maybe you have poor bonding, we've talked about that a couple of times now. Those have been introduced. You throw that with an upset condition, and pretty much at that point, that's the kind of scenario that you hear when you hear about a failure. Like I said, it's not just one thing, it's usually 2 or 3 things that are happening. And this is where you're at. So now you basically are at that 50% chance of a failure. If you're still up here, you're fine. And if that load maybe is not quite as high as you might think it could, or it could have been, you're still okay. But if you're anywhere in there, if that strength's not as high as it was, and that load is way higher than expected, that's when failures happen. So here's just another point of that. So generally, you know, the point here is just, you know, there's a reason why we have to be diligent. There's a reason why we want to have that 2 sets of eyes on our calculations, why we want to have, you know, qualified vendors and inspections and things like that. So this kind of goes back to what I started with here. So how do we maintain it? So, you know, the point here is that basically it's attention to detail throughout the whole process. So, you know, current and descriptive specs. So we just don't want to say build to RTP1. We want to drill down to each part of it. We want to say, you know, a certified manufacturer if that's the case, or we want to say materials shall be qualified per RTP1. We want to say shall be designed to RTP1, no exceptions. You know, we want to say, okay, provide an inspection and test plan. And we want to witness material testing. We want to witness fabrication points. We want to say, okay, hold points at completion of the corrosion barrier, hold points at, you know, installation of nozzles and assembly of components, and, you know, maybe final testing or something like that. You want to be very specific, exactly what you want. You know, I mentioned qualifying vendors before. You know, say, you know, pipe stress analysis, literally anything in a process, if it's above 150 degrees, should be formally analyzed in a pipe stress program. You know, everybody doesn't do that, but because I've seen lists of systems and gone through and said, okay, 3/4 of these need to be analyzed, and find out that only 25% was. But we see a lot of failures in piping particularly, and it's almost always due to poor supports and insufficient engineering. When you start seeing thermal expansion in FRP, at that point, you cannot predict the performance of that system without doing a pipe stress program. And the design reviews, like I said, fabricators do the calcs. Somebody needs to check it that really understands the standards intimately. You know, going further, it's like I said, shop inspections for new equipment. You know, you want to have, you know, you still want to go at the end when it's completed. You want to be inspecting the equipment throughout the entire process, and then finally, you want to be also witnessing the equipment testing as well. You know, we talked about qualified vendors, particularly with piping. I mean, RTP1 specifies a certain number of qualified fabricators have to be involved with the project. With piping, pretty much every laminator needs to be qualified. So you should be expecting that. That should be a point in your specifications if you have specifications for your equipment. And then more piping than tanks is you want to have that field QC element, because there's a lot going on site as well. So So that's, again, you know, it's a process. It's not just a single step. There's definitely a recipe. It's something that you do on every project. It's not material specific. You know, you need to have checks and balances in engineering and manufacturing and installation. So it's not anything different than what the owners do in the plants for steel or concrete or any other material. If you're doing concrete, you know, they take lump samples and do 28-day breaks and things like that for concrete too. You know, we need to have all the same steps in FRP, and when we do that, we generally have pretty good results. It's when we start making assumptions is when things start to go wrong. So a little bit to think about.